Okay, we're live. There we go. That sounds good. And let's start chapter 3. Okay, everybody's got the booklet? Little bit of notes. We don't write many notes in this course, but we got a little here. We have to make sure we understand what we mean when we say a specific term in math like the word factor. I'm going to say it this way. Factors are, can we read that from there? Numbers we can multiply together to make a new, I'll say value, so I don't say number over and over again. So that's what it means as, ooh, I'm going to throw some ELA at you. That's what it means when I say the word factor, and I mean it like a noun, as a thing. That's what a thing is, right? It's a piece of a number. Okay? And now I can also use the word factor as a verb. So to factor a value in math means that the value gets expressed as a set of factors that can be multiplied to make the original value. And there we go. That's what a that's the two meanings of the word factor. As a noun, it's a number that goes into another number, or that you can get out of another number by multiplying and dividing. As a verb, it means to break a number down into its smaller pieces, its factors. A prime number is a number with, and we kind of talked about this yesterday, and I just made a mistake, with two distinct factors. And the word distinct is why 1 doesn't count as a prime number. 1 only has one factor. 1 has to have two different factors. 2 is a prime number because 1 times 2 is 2. 3 is a prime number because 1 times 3 is 3. 4 is not a prime number because it's got an extra factor. It's got a 2 in it, right? So a number with two distinct factors, and those two factors are, of course, 1 and itself. And then, and this is what we played with in our game the other day, prime factorization. Prime factorization is factoring a number into a product. And remember, product just means the answer to a multiply of its prime factors. And for example, let's do 60. The prime factorization of 60 is 2 times 2, but I'm going to actually just write it like that. If I have the same factor twice, I might as well use an exponent, times 3 times 5. And I'll put a little note here. Use exponents for repeating, factors. Okay, I'll give you a second to catch up to me. I know I write fairly fast. Okay, so let's start with example 1. What is write the prime factorization of 120? And you might be going, oh, okay, well, let's see, there's a 2 in it. How many 2's are there? This is actually kind of hard to just do in your head. I mean, I just looked at 60 and I went, okay, well, it's 4 times 15. 2 times 2 times 3 times 5. 2 squared times 3 times 5. Even that wasn't easy to do in my head. So you know how we're going to approach this? And this is why, again, we played that game yesterday. Let's make a factor tree. Question? Oh, see, okay. All right. So just make sure you've got the same thing I do. Okay, so let's do 120. Factor tree for 120. Now there's multiple ways you could start this. You could start with 2. It's 2 times 60, but it's always kind of nice to start with the bigger numbers if you can notice them. Notice that it's a 10 times 12. And then 2 times 5. And then 3 times 4. And then we're not done yet. 2 times 2. So the prime factorization is 2 cubed times 3 times 5. Do you get why it's 2 cubed? Because there's 1, come on, pen. 1, 2, 3 2's, right? All right. Oh, let's go bigger. 3,300. Well, again, I think I'd start by noticing if it ends in 2 zeros, it's got to have 100 in it, right? So 33 times 100. And then 33 is just 3 and 11. Those are prime, so I'm stopped there. 100 is, well, I could just break it to 10 times 10. But that's 2 and 5 and 2 and 5. So notice that I am always putting them from smallest to biggest. Yeah, but 10's not prime, so that's not a prime factor. I have to break it down to the simplest building blocks of the number, right? If you think of numbers like they're Lego, then prime numbers are the smallest pieces that you can put together to make bigger numbers. So I wouldn't say 3 times 11 times 10 squared for 2 reasons. Reason number 1, we always go smallest to biggest. Reason number 2, 10's not done yet, right? If your teacher had said in grade 5 to make a factor tree for this number and you'd have stopped at the 10's, you'd be wrong, right? Because the branches don't end until you hit primes. So 2 squared times 3 times 5 times 11. So there's the prime factorization. Oops, thank you. Thanks for noticing that. So there we go. And if anybody wants to play the climb to a prime game with that number, is 223,000, no, sorry, is 2,235,211 a prime number? I don't know either. I'd have to go to the computer to figure that out. I don't know. Let's see. 4, 5, 6, 7, 12, 13, 14, 15, 16. It doesn't have a 3 in it. I know that. Could be prime. Well, it ends in a 1, so no. So there's no 2's, no 3's. No 5's, no 6's. Could be a 7, but you'd have to check, right? That is the thing. There is actually there's no very quick, simple way to check if a big number is prime other than to but even, okay, so you go, so a computer is doing the work that you'd have to do on paper and pencil. It's checking. You don't have to check every number smaller than that, right? There's a very nice rule that if you're checking smaller primes to see if they go into a number to see if it's prime, you can stop when you hit the value that's the square root of the number. But still, for a number this big, think about how many numbers that is. So it would be a major task to figure out if a number like this was prime. Okay, anyway. You have seen this before, I'm sure. GCF, are you okay with that if I just start calling it GCF so I don't say greatest common factor over and over again? The greatest common factor of the GCF is the largest factor that 2 or more whole numbers have in common? That's a C. There we go. For example, the GCF of 12 and 8 is 4. All right. Now, how did we come up with that 4? I don't know. I got to admit, sometimes I just look at it and it just kind of jumps out at me. But you got to kind of have an understanding of what your brain's doing. Now, I'm sure you've all heard that marvelous theory of how our brain works, that our left side of the brain is our more logical side, right? That is the side that we tend to lean on when it comes to our math skills. It's our linear thinking side. It's our logic and reasoning side of the brain. And then some people will tell you that the right side of the brain is where our artistic side is, right? That's where our creativity lies. Well, I don't have much use for creativity in my life, so I forced the right side of my brain to do some math too. So I get the left side and the right side, and I just start kind of counting on both sides. I say, hey, quick, left side of the brain, split up 12 into factors. And I say, hey, right side of the brain, split up 8 into factors. And then what's the biggest one? Oh, it's a 4. Now, could I get my brain to do that with 63 and 70? Well, probably. But it would be probably helpful if we had some sort of method that was a little more reasonable than just sort of hoping my brain finds the right number. So here's how we're going to do this. We're actually going to do this in 2 methods. Is your hand up? Oh, okay, sorry. We're going to call this one method 1. Please write down method 1 and try not to write too big because here, I'll split it in half. Yeah, method 1 on this side. Method 1 is to literally brute force method, list all factors. So we could brute force this if you like. 63. Now it's easiest to list factors if you think about them in pairs. 1 and 63. Is there a 2? No. Is there a 3? Yes. 3 and 21. Is there a 4? No. Actually, do I have to try any more even numbers? No. If 2 doesn't go into it, if it's odd, it can't have any even factors. Think about why that is. So does 5 go in? No. Does 7 go in? Yes. 7 times what? 9. So there, and that's how I know I'm done, right? They've met in the middle. I don't have to keep looking. So that's why it's easiest if you're going to make a list to just kind of work from the ends in. So let's now try 70. 1, this one has a little more. I'll give it a little more room. 70. 2, 35. Does 3 go in? What's 7 plus 0? 7. Does 3 go into 7? Doesn't go into 70 either then. So 3 doesn't go. Does 4 go? It's even. It might. Is 2's partner even? No. So then it can't have a 4. So does it have a 5? Yes. It ends in 0. So what's 5's partner? 5 what's is 70? I think it's 14. And then how about 6? No, because 3 didn't go in. How about 7? Yes. 7 and its partner is the next one, 10. So the greatest common factor of 33 and 70 is right here. Seven. Okay, what's method 2? Well, method 2 is I could make a factor tree. So for method 2, I actually go 63 is 7 times 9. And I can go 70 is 7 times 10. Now, if I was your grade 5 teacher, I'd take off marks because that's not a finished factor tree. 10 and 9 aren't prime. But in this case, I might as well just stop what I'm doing because I know right away, well, 9 is just 3's. 10 is 2 and 5. There's no factors in common in those two numbers. So the game's over. It has to be 7. Okay? All right. Let's try one that's a little tougher. And let's maybe this time, let's use the factor tree method and make a, what's the word? Make our factorizations, our prime factorization statement. So the greatest common factor of 90 and 120. So how about 90? Oops, come on, oh, pen. 90 is, let's see. Okay, it's 3 and 30, which is 3 and 3 and 10, which is 2, 3 and 3 and 5. 2, 3 and 3 and 5, right? Now let's do 120. I'm just doing the factor tree part in my head. So it's, I was going to think 12 and 10, but it's okay. 30 and 4 works. 12 and 10 breaks me down to a 2 and a 2 and a 2. So I've got 3 2s and a 3 and a 5, right? Feel free to do the actual factor tree on scrapwork if you need to. All right, so what's the greatest common factor? Well, what's common in these two parts? No, it's not 5, because there's 1 2 here, and there's at least a 2 here. There's a 3 here, and there's a couple 3s here, so they both have a 3 in common, and they both have a 5 in common. So there we go. What's common? It's like, well, how come you don't put an exponent like this 3 on here? Well, no, I can't do that, because there isn't 3 2's in the 90 number. The 90 only has 1. So it's what the smallest value is that they share. They share 2, they share 3, they share 5. The greatest common factor, somebody got it right away, it was 30. What if, however, there is 3 numbers together? Okay, let's try 3. 18, 36, and 90. Well, 18, come on, pen. Keeps kicking me out. 18 is, okay, so let's see. Again, let's make the factor tree in our head. 9 and 2, 3 and 3. 2 times 3 squared. 36. Making the factor tree in my head. 9 and 4, 3 and 3 and 2 and 2. Now I'm going to make the 90. Well, we kind of already did the 91, right? The 91 is 2 times 3 squared times 5, right? All right. What is the greatest common factor? What's common here? Well, they all have a 2. So they all have a 2. What about 3's? Yeah, they all have 3 squared. They all have 2 3's. Does that make sense to you? That you can now take this and put 2 3's down? And then that's it, right? I can't use a 5 because the 18 and the 36 don't have a 5. So that's 2 times 9 is 18. And sometimes this happens. Sometimes your GCF actually is one of the numbers you're looking for, right? A number is always a factor of itself. Don't forget that. All right, closely related, but kind of in the other direction, is the LCM, least common multiple. What do we mean by least common multiple? Well, in words, it's the smallest possible number that 2 or more whole numbers are factors of. And if you remember that when you're doing fractions in grades 7 and 8, that's what you need to think about when you want to make a common denominator. So, example, the LCM of 6 and 8. Now, once again, I'm going to use my bifurcated brain method. I'm going to say, okay, left side of the brain, count by 6's. And then right side of the brain, count by 8's. So my left side right now is going 6, 12, 18, 24. And the right side is going 8, 16, 24. And there we go. They met in the middle. They stopped because they went 24. And I, of course, am completely making up the story that I just told you. First of all, psychologists gave up on the idea that the left and right sides of your brain are that structured and definitive as to which parts of your thinking that they do. That no psychologist has thought that was reality for 50 years. We know much better. We know that your brain is far, far more complicated than that. But anyway, I got to admit, though, sometimes when I look at these, I'm not 100% sure how my brain's working. Have I seen 6 and 8 so many times in all the years of doing fractions that I just go, oh, it's 24. Okay?
The neurons made a pathway.
Exactly.
Now they're linked in your brain.
That's the way we know the brain works, right? There is a neural pathway that is so well traveled. It has had so much myelin, which is the chemical that they build the neural pathways, heaped on it. It's gone from being a little gravel road to now a superhighway. It's a bullet train that just, I don't even have to stop and think anywhere. It's an express straight from 6 and 8 to 24. I don't even really, it's not even conscious. Athletes, of course, when they don't have to think about what they do because they've done it a million times in practice, call it muscle memory. This is my math muscle memory. I've seen 6 and 8 so many times I know it's 24. But obviously, there's going to be some numbers that I haven't played with that much. There has to be a more logical, efficient algorithm way to find an LCM. So, how are we going to do this? Well, method 1 is, of course, just skip counting. Like I told my brain, I can go 6. So 6, 12, 18, 24, and then start counting the 8s. 8, 16, 24, ding. But not all numbers are easy to skip count by. So that's kind of a primitive method. We can do better. We can use factors. So here's how it works. By the factoring method, so just put that aside. The factoring method works like this. Take common factors and then multiply by unique factors. And here's what I mean by that. 12, if we factor treed that, would be 2 squared times 3, right?
Mr.
Hello.
Staff Appreciation Week. Yay!
Right, hey, very nice, thank you. Okay, hold on a sec. I'll That's okay. I will just pause what I'm doing here. We're back. Sorry about that, everybody. Okay, so 12 is a very easy factor tree, 2, 2, 3. And 10's an even easier factor tree, 2, 5. So here's how I do this. I'm going to get a highlighter here. What's the common part? Well, the common part is they both have a 2, right? So the common factor part is the 2. But then I have to do everything else. Right? So this is, again, this is the common part. And then this is the unique part. And I just misspelled unique. Unique. So it's 4 times 3 times 5? 60. And there might be people who go, wait a minute, isn't 120? Don't I just take the numbers and times them together? Now, the reason why sometimes I get grade 10s who say, the last example, wait a minute, 6 and 8, it's the lowest common multiple is 48. And they just, it takes some convincing. No, it's not, it's 24. Because you know what happens is, if you were actually in the world of, don't write this down, if you were in the world of fractions, and you were lazy and just went, oh, it's just 6 times 8 is 48. You get this, right? And this will get you the right answer. You just have to simplify it. So they got into the habit of not having to think about what the lowest common multiple is really, because you can get the right answer without having to do that. But in the math we're going to be doing, we need to know the lowest common multiple, right? So we do have to actually find the best number, the smallest number. We can't just go, oh, 10 times 12 is 120. There you go. 12 and 10 are both in 120. Let's move on. No, it doesn't work that way. We need to know the lowest common. So now let's try one with 3. 18, 20, and 30. So 18, we've already seen 18 today. 18 is 2 times 3 squared. 20 is 2 squared times 5. And 30 is 2 times 3 times 5. Okay. What's common here? Now, remember it only has to be actually common amongst two things. It doesn't have to be common to all three. So what's common here to the two things? Well, the common one is I have a 2 in all three things. So 1, 2, 3, there's that 2. In fact, you know what I'm going to do? I'm going to cancel them out as I go. So I'm going to take a red pen here, and I'm going to say, okay, I'm canceling that 2, and one of these 2's. See what I did there? Leaves behind the other 2. And there it is. Now I'm writing it down. There, 2. There's my common 2. Okay? Now what else is there? There's a 3 that is common. So I'm going to cancel out that 2, that exponent, and that 3 there. That took care of one of the 3's in the first one and the 3 in the 30. So 2 times 3. What else is common?
5.
A 5. You and you are now represented right here. So there's my commons. Is there anything else common? No. All I'm left with is a 3 from the 18 and a 2 from the 20. So now my uniques. So there's my commons, and now here's my uniques. I'll use a different color. I'll just underline. The 3 that's left over and the 2 that's left over are right here. Now I have to multiply all that together. Let's see, is there an easy way to do it? Yeah, do the 2 times the 5 first. Or actually, do the 2 times the 5 last, because it's easy to times a number by 10. Just slap a 0 on it, right? So it's going to be 3 times 3 times 2. So that's 18 times a 10. And if you're wondering, why is he, do you get suspicious when your math teacher starts talking that way? Wait a minute, he's looking for mental math tricks. Oh no, that means we don't get a calculator on the test. Very wise of you. That's good pattern recognition you got there. Yes, we do test this stuff without a calculator. We want you to move on to pre-cal and even applied with some number skills. It's important. Yes, you always have a device on you that has a calculator, but it is important that you can work with numbers with some confidence and some ability to not have to rely on that device for every little thing you do, because it really does slow down your thinking, right? The ability to work with numbers means the ability to think with numbers. So, yep, we're going to teach this stuff and not make you have a calculator. To be honest, there isn't really any mental math in this course, because mental math would mean I don't let you have paper either, right? I actually did have a parent once come in and said, this is really unfair. In junior high, my child was allowed a calculator, and they never had to do mental math. I said, they don't have to do mental math now. They get scrap paper. Just made her madder. Didn't help. Didn't help the conversation any. I have had students who literally, they had an adaptation plan to their work, and they did have a calculator. And even then, you know what? I don't want you to use a calculator for most of the stuff we do in this course. How about I give you a times table? Because that way you can at least get the physical patterns of your brain of having to look numbers up on the times table.
Well, that's like giving a periodic table.
Kind of.
During a chem test.
Kind of. Well, we don't make you memorize the periodic table. What's that?
Totally cheating, but definitely useful.
It's useful, yeah. But again, the idea is that hopefully that's a temporary fix. The idea is that everybody should be comfortable enough with numbers that something like this shouldn't lead you to have to run to your calculator. I would hope. Okay, having said that, here's a tougher one. So 28. What's 28's prime factorization? There's a 4 and a 7. 2 squared times 7. 42. Come on, pen. 42 is a 6 and a 7, so that's a 2 and a 3 and a 7. And 63, I think we did that one already today. That one's a 3 times a 2 times a 7. So, right, 2 times 3 times 7. No, wait a minute. Let's do that again. 21 times 3. It's 3 times 3 times 7. 3, come on. 3 squared times 7. There we go. Looking good. Now what? All right, I'm going to do it the same way I did the other one. First, what are my commons? A 2 and a 2. And notice again what I just crossed out. Do you get the idea of crossing out the exponent just leaves behind the base? But I'm not really crossing out the exponent. I'm crossing out the base. It's just the base happens twice. Okay? Now I'm going to do a 3 that's common. This 3 is common to one of these 3's. Get it? So there, times a 3. What else is common? All 3 of them have a 7. So I only have to count it once. Come on. There we go. And then others. What's left? Well, the 28 still has a 2. The 63 still has a 3. Okay. 7's not a pleasant number to work with, but you know what's easy is doubling numbers is easy. Why don't you leave the 2's till the end? So 7 times 9 is what? 63 doubled. 126. Now double it again. 252. There you go. See? And I didn't even let you use scrap paper. Nice work. Okay? All right. That was the end of example 8. And that actually is the end of the first lesson. So I'm going to turn off the video now, because that's what I'll post online for the people who might have missed part of it. If you were at home and it's like, my Wi-Fi died for 20 minutes and I can't catch up on these notes, you can always go to the video. It'll be up in a little while. Come on.